Okay, let's talk about this thing. We all have one, right? It's that little black box that's always kind of hanging around between the wall and our laptop, quietly powering our entire digital world. But behind that plain-looking box is a little marvel of engineering that's way more clever than you'd probably guess.
Yeah, you might call it a power brick, maybe a wall wart, or just the AC adapter. Whatever you call it, this thing is the unsung hero, the crucial link between the giant, powerful electrical grid and the super delicate electronics inside your computer.
But have you ever really stopped to think about it? I mean, what is actually going on inside that little plastic case to make everything work? Well, today we're going to crack it open, metaphorically, of course, and see what's what. So, the number one job for any charger is to tame the raw, wild power that comes surging out of your wall socket. It's kind of like trying to give a tiny, delicate plant a drink from a fire hose. You can't just blast it. You need something in the middle to get the pressure just right.
And here's the heart of the problem. The power from your wall is alternating current, or AC. It's high voltage, and it's constantly flipping direction back and forth 50 or 60 times every second. It's powerful, sure, but it's totally useless for your laptop. Your laptop needs direct current, or DC, a super stable, gentle, and really precise little stream of energy.
Now, the old school way of doing this involved these things called linear power supplies. And maybe you remember them. They were basically giant, heavy transformers that got incredibly hot and were just terribly inefficient. Today, pretty much every charger you own uses what's called a switched mode power supply, or SMPS. These things are lightweight, they stay cool, and they are amazingly efficient.
So, let's take a little journey inside one of these modern adapters to see how this high-tech magic happens. It's actually a really elegant four-step dance.
Okay, so it all happens in 4 key stages. First, that wild AC from the wall gets rectified. Basically, it's forced to flow in only one direction, which turns it into a high voltage, but still kind of lumpy DC current. Then, and this is the clever part, a tiny electronic switch, a transistor, starts flipping on and off at an insane speed, hundreds of thousands of times every second. This super fast chopping action creates a high-frequency signal, which can then go through a much smaller, way more efficient transformer. That transformer steps the voltage way down. Finally, this new low-voltage power gets rectified again, and then it's smoothed out by other parts, delivering that perfectly clean, stable power your laptop needs to survive.
A really great way to think about this high-speed switching is like this. Instead of taking one big, sloppy, inefficient gulp of power from the wall, the charger takes hundreds of thousands of tiny, efficient little sips every second. That is the whole secret behind a modern power supply.
But, this whole sipping process creates a bit of a headache for the power grid itself. Because the charger is only grabbing power in these short little bursts, it can actually look really inefficient from the grid's point of view, creating something called a low power factor.
And the solution is often explained with this fantastic frothy beer analogy. A low power factor is like getting a beer that's mostly foam. Yeah, the glass is full, but you're not getting much actual beer. So modern chargers have a special circuit inside called power factor correction, or PFC. Think of it like a good bartender who lets the foam settle, making sure the grid is delivering almost all liquid, real power, and very little wasted foam.
Okay, let's solve another mystery. What is that little cylinder, that lump that you always see near the end of the power cord? I promise, it's not just there for looks.
That thing is called a ferrite bead. All that high-frequency switching going on inside the charger creates a ton of electronic noise. Without this bead, your power cord would act like a little radio antenna, broadcasting that noise all over the place and potentially messing with your Wi-Fi or other wireless devices. The ferrite bead just soaks up all that noise and turns it into a tiny bit of heat, keeping your airwaves nice and clean.
So, over the years, these power bricks have gotten smaller and smaller and smaller. And this isn't just about making them easier to carry. It's the result of some really incredible engineering.
The first big secret to making them tiny was that high-frequency switching we keep talking about. And here's the key idea. It's like a fundamental law of electronics. The higher the frequency you switch at, the smaller the transformer you need to get the job done. So as engineers cranked up the switching speeds, those old bulky iron parts could be swapped out for tiny, tiny ferrite components. But even good old silicon transistors can only go so fast. The real game changer, the thing that's made today's tiny chargers possible, is a new material, gallium nitride, or GaN. GaN transistors can switch way faster, they can handle more power, and, this is crucial, they waste far less energy as heat.
And less heat means you don't need big metal fins to cool things down, letting engineers cram everything into a much smaller package.
So what does this all mean for you? Well, by making the switch from silicon to gallium nitride, companies can make chargers that are up to 40% smaller and lighter than the old ones. That is a huge leap forward in what we call power density.
And this whole evolution in size and efficiency, it's paved the way for something that a lot of us have been dreaming about for years, a truly universal charger. And it might be leading to a future where the charger just disappears completely.
I mean, the road to getting one single charger has been a long one. Remember the drawer full of random power plugs for every device? We've gone from that tangled mess to the arrival of the awesome universal USB-C connector. With new standards built in, one single cable can now talk to your device and deliver exactly the right amount of power. And with new rules coming into effect, this universal dream is finally becoming a reality for everyone.
And the latest standard, USB Power Delivery 3.1, is an absolute powerhouse. It can push up to 240 watts of power. That is more than enough to charge even the biggest, most power-hungry gaming laptops, all through that one tiny, reversible USB-C cable. It's amazing.
But the story doesn't stop with just one cable to rule them all. Nope. The true holy grail, the ultimate goal here, is to get rid of the physical connection altogether.
And this quote just says it all, doesn't it? The vision is total freedom. No more plugging in, no more hunting for an open outlet, just liberation from the tyranny of the charging cable. And this isn't science fiction anymore. Companies are already developing systems that use smart antennas to safely beam power right through the air. A transmitter could find your laptop in a room and send a focused beam of energy to charge it, with no wires, no contact, nothing.
And that leaves us with a pretty wild final thought. We've watched the charger shrink from a heavy brick to a tiny plug. So is its final form to just become completely invisible? Could the next charger just be the room that you happen to be sitting in?
Don't forget to like and subscribe for more How Meets History.